Hi everyone! Welcome to the second session of our PLC programming tutorial. In the previous session, we explored the power supply and Siemens S7-300 CPUs. Today, we'll take a closer look at digital and analog input and output modules, followed by a discussion on wiring digital input and output modules. Let's get started. PLC CPUs operate using binary values. To interact with the external environment, PLCs require input and output modules. Input modules receive signals from the field, convert them into binary values zeros and ones that the CPU can process, and then transmit them to the CPU. Conversely, output modules receive signals from the CPU and send them to actuators to control various processes. Now, let's explore the different types of input and output signals. If anything is unclear, don't worry. Stay with me until the end of the video, and I'll break everything down for you step by step. By the end, you'll have a clear understanding and the confidence to apply what you've learned. PLC inputs can be categorized into two main types: digital inputs and analog inputs, depending on the type of signals they receive from field devices. First, let's look at digital inputs. Digital inputs work in a binary manner, meaning they can only detect two states, on or off. When the input is on, it means the signal is active, and when it's off, the signal is inactive. This simplicity makes digital inputs ideal for on-off operations. Examples of digital inputs: start and stop buttons like push buttons for controlling a machine. Limit switches, which are used for detecting mechanical positions. Inductive and capacitive sensors, commonly used for object detection in automated systems. These inputs are crucial for simple control systems, where you only need to know if something is activated or not. Now, let's talk about analog inputs. Unlike digital inputs, which are binary, analog inputs can detect a continuous range of values, allowing the PLC to monitor varying signals like temperature, pressure, or speed over time. Common signal ranges for analog inputs: voltage, typically ranging from 0 to 10 volt. Current, the most common range is 4 to 20 milliamp, which is preferred in industrial environments because it is more resistant to electrical noise and can transmit signals over long distances without losing accuracy. Some analog sensors, such as thermocouples or RTDs for temperature measurement, require special input modules that condition the signal and compensate for temperature variations. Just like inputs, PLC outputs are also divided into digital and analog categories. These outputs control various devices in an automation system, either turning them on or off, or providing continuous control. Let's start with digital outputs. Similar to digital inputs, these outputs can be either on or off. When a digital output is on, it activates a connected device. When it's off, the device is deactivated. Examples of digital outputs: relays and contactors, used for switching devices like motors, pumps, or lights on or off. Solenoid valves, which control the flow of liquids or gases. Indicators or alarms, used to show system status or alert operators. Now, let's move on to analog outputs. Unlike digital outputs, analog outputs do not have just two fixed states. These outputs provide continuous control signals that vary in value to control devices precisely. Examples of analog outputs: voltage-based outputs, for example 0 to 10 volt, used to control devices like variable speed drives, adjusting the speed of motors. Current-based outputs, for example 4 to 20 milliamp, commonly used for controlling actuators, valves, or motor speeds in industrial applications. Understanding the difference between these types of inputs and outputs is fundamental for designing and programming PLC systems efficiently. In this image, you can see input and output modules connected to the S7-300 PLC. Each module is identified by a unique code that indicates its function and type. Each I/O module in the S7-300 series has a specific identification code. This code provides detailed information about the module, such as its function, type, and whether it's an input or output module. Let's break down the structure of a typical module code. SM321. The module code SM321 can be broken down as follows. S stands for signal module, indicating that this is an input or output module. M indicates that this is a module. 321 represents the specific module number, which tells us whether it's a digital input, digital output, analog input, or analog output. The structure of the SM module code in the S7-300 series follows this format. SM3 axis. The first digit 3. This indicates that the module belongs to the S7-300 series. The second digit X. This digit tells us whether the module is digital or analog. If X equals 2, it refers to a digital module. If X equals 3, it refers to an analog module. The third digit Y. This digit specifies whether the module is an input or output. If Y equals 1, it refers to an input module. If Y equals 2, it refers to an output module. Here are some examples to help you understand how the module codes work. SM321, digital input module. SM322, digital output module. SM331, analog input module. SM332, analog output module. Let's continue with the SM321 module. The SM321 is a digital input module in the S7-300 PLC series. It receives signals from field devices, such as push buttons, limit switches, and sensors, and converts these signals into a format that the CPU can process. The number of inputs available in the SM321 module can be 8, 16, 32, or 64. The choice of module depends on the project's requirements and the number of digital input signals needed. Another important factor to consider is the input voltage rating of the digital module. This rating determines the voltage levels that can be connected to the module. Digital input modules are available in different voltage ranges, including 24-volt DC, the most common voltage used in industrial automation; 120-volt AC, often used in control systems where 120-volt AC signals are standard; 230-volt AC, typically found in high-power control applications. Before connecting input devices, it is essential to verify the module's voltage specifications to ensure compatibility with your system. Since we will start programming in the next video and test our project with real hardware, it is crucial to understand the correct wiring of the SM321 digital input module. This module has 16 digital inputs and operates at 24-volt DC. Now, let's take a closer look at its wiring configuration. When you open the module cover, you will find a wiring diagram printed on the inside. This diagram guides us on how to correctly wire the module to ensure proper operation. The module has 20 terminals in total. Terminal 1 is empty and not used in wiring. Terminal 10 and Terminal 11 are also unused. Terminal 20 must be connected to the -M terminal of the power supply. To properly activate the inputs, follow these steps. 1. Connect the -M terminal of the power supply to Terminal 20. 2. Connect the +L+ terminal of the power supply to one side of the input device, such as push button, limit switch, or sensor. 3. Connect the other side of the input device to one of the input terminals, terminals 2 to 9, or terminals 12 to 19. When the input device is activated, for example, a push button is pressed, the corresponding input receives a 24-volt signal, changing its state to logic high 1 in the PLC program. As you can see, Each terminal is equipped with an LED indicator. These LEDs light up when the corresponding input is active, providing a visual indication of the input status. For example, in this setup, when the start button is pressed, the LED next to the corresponding input terminal will turn on, signaling that the input is now active. This action sends a high-pulse logic 1 to the CPU, indicating that the input has been triggered. This wiring configuration ensures that the PLC correctly detects input signals from external devices, allowing it to respond accordingly in the control program. One important piece of equipment used in industrial automation is sensors. All sensors follow a standard wiring rule. Now, let's wire a photosensor to a digital input module. A photosensor typically has 3 main wires with the following color codes. Brown wire connected to the positive L+ terminal of the power supply. Blue wire connected to the negative M terminal of the power supply. Black wire. This is the output signal wire, which determines whether the sensor operates in PNP or NPN mode. I will explain this later. Additionally, some photosensors have a 4th wire white, which is used to select light on or dark on mode. I will explain this function when working with real hardware, so we won't focus on it in this section. Now, let's wire this sensor step by step. 1. Connect the negative M terminal of the power supply to the blue wire of the sensor, and also to terminal 20 of the input module. 2. Connect the positive L+ terminal of the power supply to the brown wire of the sensor. 3. Connect the black output wire of the sensor to the required input terminal on the module. In this example, I am connecting it to input terminal 2. Now, the wiring is complete. When the sensor detects an object, it sends a signal to the input module. This activates the corresponding input, turning on the LED indicator on the module and sending a high pulse to the CPU. SM322 Digital Output Module. The SM322 is a digital output module in the S7-300 PLC series. It allows the PLC to send control signals to field devices such as relays, solenoid valves, contactors, indicator lamps. This module plays a critical role in industrial automation by switching connected devices on or off based on the PLC's logic. The SM322 module comes in different configurations based on the number of digital outputs available. 8 outputs, 16 outputs, 32 outputs, 64 outputs. The choice of module depends on the project requirements and the number of actuators that need to be controlled. The SM322 module is available in 2 main output types. 1. Relay outputs. Suitable for both AC and DC loads. Can control high-power devices. Slower switching time compared to transistor outputs. Provides electrical isolation between the PLC and the field device. 2. Transistor outputs. Can only be used with DC loads. Faster switching time, ideal for high-speed applications. Key differences between relay and transistor outputs. Relay outputs are better suited for high-power AC or DC loads, where fast switching is not necessary. Transistor outputs are preferred for fast-switching DC loads, such as pulse signals in high-speed applications. Relay output modules have the label REL on the module, indicating it is a relay-based output. Transistor output modules do not have this label. The module shown in the image has 32 digital outputs and operates at 24-volt DC. Now, let's move on to wiring the SM322 digital output module. In this example, we have a SM322 module, and we will go through the proper wiring process step by step. When you open the module cover, you will see a printed wiring diagram inside. This diagram provides instructions on how to correctly connect the module. The SM322 digital output module operates at 24-volt DC and uses transistor PNP outputs. Here are the key points to keep in mind. The module provides a positive voltage plus 24 volt on its outputs. One side of the load is connected to the module, while the other side example relay coil must be connected to the negative M terminal of the power supply. You cannot connect AC loads directly to this module. To control AC devices, you must use a 24-volt DC relay between the module and the AC load. The outputs are divided into 4 channels, and each channel must be powered separately. If a channel is not powered, the outputs in that channel will not work, even if the PLC sends a signal. To power channel 1, follow these steps. 1. Connect terminal 1 to the positive L plus terminal of the power supply. 2. Connect terminal 10 to the negative M terminal of the power supply. Now, channel 1 is powered and ready to use. To control an AC load, we must first wire a relay to one of the module's outputs. After that, the AC load, such as a contactor, will be connected to the relay. For example, you cannot connect a 230-volt AC contactor directly to this module because the SM322 output operates at 24-volt DC. Instead, you must first connect a 24-volt DC relay to the module output, and then connect the AC contactor to the relay. When the PLC output is activated, it will energize the relay, which in turn will switch the contactor and control the AC load. According to the wiring diagram, the relay coil must be connected as follows. Connect the AON terminal positive side of the relay coil to the output terminal on the SM322 module. Connect the ATWO terminal negative side of the relay coil to the negative M terminal of the power supply. Step-by-step wiring. At this point, when the PLC activates output 2, the relay will be energized, allowing you to control an external AC device. If you need to use another channel, you must power it separately. 1. Connect terminal 11 to the positive L plus terminal of the power supply. 2. Connect terminal 20 to the negative M terminal of the power supply. Now, channel 2 is powered and ready to use. To connect another relay to channel 2, follow these steps. 1. Connect ATWO of the second relay to the negative M terminal of the power supply. 2. Connect AON of the relay coil to terminal 12 on the output module. Now, this relay is also ready to control another external device when its corresponding output is activated. Now, we have successfully wired the SM322 digital output module with relays to control external devices. SM331 Analog Input Module. The SM331 is an analog input module in the S7-300 PLC series. It enables the PLC to receive continuous analog signals from field devices such as transmitters, example, pressure, flow, and level transmitters, temperature sensors, RTDs, thermocouples, position sensors, other process measurement instruments. How it works. The SM331 module converts analog signals into digital data that the CPU can process. Since the CPU cannot directly handle analog signals, this conversion process is called analog to digital A to D conversion. The module's role is to ensure that continuous real-world analog signals are converted into digital values that the PLC can use for control and monitoring. The number of analog inputs in an SM331 module depends on the specific module variant. Common configurations are 2 inputs, 4 inputs, X inputs. The number of inputs you choose depends on the specific needs of the project and how many analog signals must be processed. The resolution of an analog input module is a crucial factor that determines the precision with which analog signals are measured. Resolution is measured in bits, and the SM331 module typically offers 12-bit, 13-bit, 14-bit, 16-bit. A higher resolution provides greater accuracy in converting analog signals to digital form. For example, a 16-bit resolution allows for finer distinctions between values, which is essential for high-precision tasks like temperature or pressure measurements. The higher the bit value, the more precise the measurement. In this case, this module is a 12-bit resolution analog input module with 8 inputs. In the next section, we will dive deeper into how resolution affects the performance and accuracy of analog signals. SM332 Analog Output Module. The SM332 is an analog output module in the S7-300 PLC series. It enables the PLC to send continuous analog signals to field devices, a process known as digital to analog D to A conversion. This module is used to control processes that require continuous, variable control signals. Unlike digital outputs, which only provide on-off signals, analog outputs are used for applications where precise, adjustable control is needed. Common applications include variable frequency, drives VFDs, to control motor speed dynamically, positioner valves, to regulate flow, pressure, or steam control. The SM332 module is available in several configurations based on the number of analog outputs. 2 outputs, 4 outputs, 8 outputs. The selection depends on the number of devices that need to be controlled and the specific automation system requirements. Types of analog output signals. The SM332 module supports various types of analog output signals to match the needs of different field devices. 1. Voltage signals. 0 to 10 volt, 1 to 5 volt, etc. These are used for devices that accept voltage-based control signals. 2. Current signals. 0 to 20 milliamp, 4 to 20 milliamp. These are commonly used in industrial automation because they offer better noise resistance, especially for long-distance signal transmission. Current signals are less susceptible to electrical noise, making them ideal for industrial environments. Wiring of the analog module is a little different from the digital module. First, you need to have information about the type of sensor you're using, and based on the sensor, you will do the wiring. I will discuss this part in the analog inputs section of the programming video. In the S7-300 PLC, the rack is used to house the modules. It is made of aluminum and serves only as mechanical support for the modules. It does not provide electrical connections between them. For electrical connections, the system uses a bus connector, which enables communication between the modules. The rack comes in different sizes, and its selection depends on the number of modules required for the project. A larger rack can be cut to the required size if necessary. Each rack is divided into 11 slots, where different modules can be placed. Each module must be placed in the correct slot according to a predefined positioning rule. Let's break down these rules and understand how modules should be arranged in the rack. As mentioned earlier, each S7-300 PLC rack supports up to 11 modules. These slots are predefined positions, and you must follow specific rules when placing the modules. If the modules are placed incorrectly, the hardware configuration in the PLC program will not allow the system to function properly. Slot allocation rules. Slot 1 power supply module, optional. This slot is reserved for the power supply module. It is optional. You can leave this slot empty if an external power source is used. Slot 2 CPU module mandatory. This slot is specifically for the CPU module. You must select the correct CPU model in the hardware configuration to match the real hardware. Each module has a specific order number, which must match the configuration in the software. Slot 3 IM interface module, if used. If the system has multiple racks, an IM interface module is placed here. I will explain the interface module in more detail later. Slots 4 to 11. Other modules. These slots can be used for various expansion modules. Signal modules SIMM. Digital or analog input-output modules. CP communication processor modules. If the CPU does not support an industrial network example, Profibus or PROFINET, a CP module can be added to enable network communication. FM function modules. These modules provide specialized functions, such as high-speed counters, motion control, or advanced processing. CP. Communication processor modules help the CPU communicate with external devices via different industrial networks. FM function modules provide additional features to the PLC. For example, if the project requires high-speed counting, an FM module is used to assist the CPU in handling this function efficiently. Expanding the S7-300 PLC system with multiple racks. In large-scale projects, a single rack may not be enough to accommodate all the input and output modules. If the number of input and output modules exceeds the capacity of one rack, we can expand the system by adding more racks. To connect additional racks to the CPU, we use an IM interface module. IM interface module purpose. Connects an expansion rack to the main master rack. Ensures proper communication between the CPU and additional racks. Allows the PLC to manage more I/O modules without performance issues. If the second rack also does not support all the required modules, we can add a third rack. The third rack is connected to the second rack using another IM module. This process can be repeated to add up to 4 racks in total. Each CPU in the S7-300 series can support up to 4 racks. 1 master rack where the CPU is located. 3 additional expansion racks, each connected using an IM module. This modular expansion system allows the PLC to handle larger and more complex automation projects efficiently. In the hardware configuration within Siemens Step 7 software, if there is no expansion rack, we must leave that slot 3 empty in the configuration. However, in real hardware, all modules must be physically connected without any gaps. If I don't need to use an expansion rack and only have 1 rack, how many modules can be placed in this rack? Please leave your answer in the comments. Another important requirement is the bus connector. As I mentioned earlier, the rack in the S7-300 PLC is only used for housing the modules. It does not provide electrical connections between them. To establish communication between the modules and the CPU, we need to use a bus connector. In this picture, you can see the bus connector. Before mounting the modules in the rack, it is essential to install the bus connector to ensure proper communication between the modules and the CPU. In this video and the previous one, I talked about the essential hardware requirements for the S7-300 PLC. With this hardware, we can start working on a real project. However, we will continue discussing the hardware section alongside the programming videos. First, we need to use and understand the basic hardware in real-world applications. Later, we will cover the remaining modules at an advanced level. In the next video, we will begin programming and start with a practical project, controlling an electric motor using a PLC. Don't miss it. I hope you found this video useful. Please support my channel by subscribing, liking, and commenting. If you have any questions, feel free to leave a comment. I will be happy to answer them. Your support helps me improve my future videos. Stay tuned for more content. After these videos, I promise you will be able to work on real-world projects with confidence. And if you ever face challenges in any project, anywhere in the world, I will be by your side, guiding you step by step.